Okay, here we go. So, derivatives. Okay, time shift into math mode here for just a little bit. So, derivatives. So, we said yesterday we had a definition of the derivative. What was it?
You want the equation?
Yeah, but don't look. You can just tell me. What was it?
Parentheses x.
Well, the limit.
Limit, sorry.
Yeah.
Parentheses x plus delta x.
Okay, so that's f of x plus delta x.
Minus f of x. All over delta x as delta x in parentheses.
Ooh, got it. Good. Okay, good. And I want you to not forget where that came from, right? All that is, the pictures in calculus are huge. This is a picture theorem, I call these things, right? This is, a picture describes the whole thing.
Is there a song for this one too?
Probably. I don't have a song for this. Remember, all this is we're just saying if I go from x over to x plus delta x, all we're doing is we're taking the slope of the secant line and taking the limit as delta x goes to 0, so the points converge, and the secant line becomes a tangent, right? That's it. That's our strategy. Okay, so we looked at an example of that. I'm not going to go through another one. You guys will get plenty of practice with that stuff. There is another way to do this, and I don't want to spend a ton of time on this because this, like many things we'll do this year in calculus, is a first step. It's kind of a precursor to a much easier way of doing derivatives. And so we don't really need to become amazing experts on taking derivatives using limits because you're almost never ever going to do that. Okay? But there is another way to do it. We could just redraw the picture, right? We could draw the picture instead of drawing it in terms of x and x plus delta x. We could do the same thing, but we could call this something like x and c, for example. Okay? And then this point right here would have coordinates x, f of x, right? And this point right here would have coordinates what? C,
F of x plus delta x.
f of, well, f of c. We'll just call that x value c. Okay, and actually, I'm going to mix them around. Not that it makes any difference except the one small difference it makes is it makes the formula just a little bit easier to work with. But it really doesn't make any difference which one we call x and which one we call c. But I will flip them around. So let's call this one c, and let's call this one x. But it's still, we just are defining a secant line, right? How are we going to change the limit, though, in this case? If we want the secant line to become a tangent, the slope of this secant line, we could still write as just rise over run. Well, what's the rise?
X minus F of C.
Everybody agree? This y value minus that y value over run.
X of C. Or minus C.
Okay. What's my limit going to be then, probably? As we could either do, there's two ways we could do this. We could either write it as x approaches c or c approaches x, but we're used to saying as x approaches something, so we'll just do that as x approaches c. Okay. And then that's going to give us 0 over 0, but that's going to, which we need, right? It's going to make that interval converge to a single point. Why would we do that? Just because it sometimes makes the algebra a little bit easier than doing it this way. That's it. Nothing super profound. Any derivative that we could take this way, we could also take this way, and vice versa. It's just that sometimes this makes things just a little bit simpler for certain situations. Very few, but we might take advantage of that today. So the real topic that I have for today that I want to talk to you about is differentiability. Okay, there's two. So here's our kind of refresher on what the definition of derivative is. We added one more form for that. Not hard to apply. You'll get some practice. But we want to talk about two things. Differentiability and What do you think differentiability is? Okay, well, kind of. When we have a derivative, if we want to take a derivative is a noun, okay? The verb that goes with derivative is differentiate. So differentiate means the act of taking a derivative. To take a derivative is to differentiate, okay? So differentiability means literally kind of take the derivative ability, right? Can we, where are we able to take a derivative? A function is differentiable wherever we could take a derivative. Okay, but there are going to be some places where derivatives are undefined, and we started to just get a hint of that a little bit yesterday, right? So let's look at a couple examples like that. Let's take something like, let's take something like an absolute value function. Okay. If I want to differentiate this, to take the derivative of this, how might I do that? Absolute value functions are a little bit tricky and a little bit of a pain. Because, go ahead.
Would it just be a straight line?
Well, okay, but the thing about an absolute value function is, and you've had a little bit of experience with this in honors algebra 2, probably quite a bit, and then a little bit last year too. You can't always do all the algebra you need to conveniently with absolute value notation, right? Because absolute value notation does kind of two separate things in different places, right? And so when functions behave that way, when they have different behaviors for different values of x, what does that sound like? Because I mean, if we put a positive argument into an absolute value function, it doesn't do anything, right? But if it's negative, well, then it does. It has to multiply by -1 to make it positive. That's its only job, right? Is to ensure that the output is positive.
So it's like when you can take a limit because the ants wouldn't know where they were going.
Well, okay, that's what we're going to see graphically, yeah, but just even more generally than that, if we've got a function that has that kind of disparate behavior like that, well, maybe, but how are we even going to express the function if it's got different behaviors?
Piecewise.
Piecewise, yeah, right? It's going to be a piece. Does that make sense? How that fits the bill here? So this needs to be a piecewise function, right? And the way we're going to write this might be a little different. I can't remember what you guys probably did in algebra 2, but either way works. We're going to write this as 3 pieces. We're going to write it as 2 big pieces and then the boundary between the 2. Right? So what does this function do whenever hand is positive?
It's going to be positive.
It's not going to do anything, right? If hand is positive, then the absolute value of hand is just hand, right? So this function is equal to x minus 2 whenever x minus 2 is greater than 0, right? Well, saying x minus 2 is greater than 0 is not a convenient way to say that, though. When we're writing a piecewise function, we want to be able to write the subdomains in terms of x's, right? So what would I do to solve for x there?
X is greater than 2.
X is greater than 2. Just add 2 to both sides. And we get the result, x is greater than 2. So on that domain, that's the value of the piecewise function, the absolute value function. Well, what's the absolute value of 0? 0. So this is equal to 0 whenever x minus 2 equals 0, which is when? X equals 2. And it equals the opposite of hand, right? If hand is negative. So we get negative the quantity x minus 2 whenever x minus 2 is less than 0, which we could more easily write as x is
Greater than 2.
less than 2, right? Okay, makes sense? And we know what that looks like, right? If we were to graph this thing, we know what it looks like. This is just an absolute value v what does it do if I subtract 2 from x inside the function? What am I doing? What kind of transformation is that? Moving it right by 2, isn't it? H is, so the parameter h is equal to 2, and h is responsible for horizontal translations, okay? So we just scoot over 2, and then we're gonna get let's make this one. Okay, so those are the 3 pieces, color-coded, right? So let's go ahead and do a derivative, right? Let's do the derivative by inspection, though. Let's not go through the whole process. We can just look at this graph and determine what the slopes are, because that's what the derivative means, right? It's the slope of the function. Agree? So if we want to do a derivative function, then we're going to differentiate. And we're going to get f prime of x equals what? So for values of x greater than 2, what's the slope? Well, 1. 1. So it equals 1 whenever x is greater than 2. What's the slope over here? Negative 1 when x is less than 2, right? And what's that mean about the middle? Yeah, it doesn't work, does it? It's not going to work. We can show it algebraically. I'm not going to. I mean, we don't really need to, do we? Because we can see that in the middle, I've got a dilemma here. I've got 2 different slopes. So we can just kind of, physics would say we're going to do some hand waving here. We're going to finesse our way through this. If the ant is standing on that blue point right there, he could conceivably define his slope if he steps to the right as being 1 or to the left as negative 1. Okay, but that can't be, right? You can't have multiple slopes at a single point, right? And so what must we say? It's undefined. Yeah, the derivative doesn't exist there, right? At 0. Oh, actually, hang on. Get it backwards. It's undefined at x equals 0. Here's another way of looking at that. This is one of the really cool things about math. I just love this about math. Is that, and I kind of enjoy just, this is one of the best parts of teaching, is you get to kind of think about different ways to conceptualize this. Well, here's another way. Think what a derivative means. A derivative is the slope of a tangent line, right? Well, what is a tangent line? Now think back, we had a discussion about this a little bit ago. If I've got any curve, and I want to know what the slope of the tangent line is at some value of x, well, then all I've got to do is find the tangent line. But what is the tangent line? If I focus in on this point infinitely, what happens to the black curvature?
Goes away.
It goes away, right? Would everybody agree if I kept zooming in and zooming in and zooming in, the black curve and the red line would eventually look one and the same, right? And so for that reason, doesn't it make sense that we could define a slope of the curve at that point, right? Because if I zoom in, we will see that the curve actually becomes that line, and we know slope is a quality of a line, right? So therefore, we can say it's a quality of the curve at that point, okay? What's the problem, though, at this point right here? If I zoom in closer and closer and closer, what happens to that, the part of the curve around the vertex?
Stays the same.
Stays the same. It never flattens out, does it? It always looks like the same V on any scale, right? So it's fractal in that way, right? And so therefore, there's another way we could say, swing and a miss, right? It doesn't act tangentially, and that's what a derivative means. We can also show it algebraically if we did a limit, but I'm going to resist the temptation because we'll look at something else maybe instead. So in general, this is a type of a place where functions fail to be differentiable. What was it? What might we call that feature there?
The vertex.
Okay, so it's a, how about if we call it a sharp turn, or sharp, right, sharp corner would be better, sharp corner. Someplace, if it's a sharp corner, that means that regardless of how far I zoom in, it's never gonna flatten out, right? And so there's one place where functions are not differentiable, sharp corners. Okay, let's look at another one.
Mr. Roy?
Yeah.
Can you go back to the last one?
Sure.
Great in pointing this out. For the undefined, wouldn't it be x equals 2?
Oh, you're right. Thank you. Yep, it's that too. Okay, so here's something we could do then. We did a couple of these yesterday where I gave you a function, you graphed the derivative, right? At the end of the day. Let's graph the derivative in green. What's it going to look like?
It's just the
Yeah.
same thing.
So what's the graph going to be for the graph of the derivative going to look like for the red part?
Just the straight line that's already.
But what's the remember the value of the derivative equals the slope of the function. What's the slope of the function there? Negative 1, right? Okay, so then we've got the derivative function is just going to look like that, right? And that's only including values less than 2. What does it look like for values greater than 2? Positive. And then what happens at 2? Fine. And we have a hole there. Okay. All right. Different function. Let's look at our greatest integer function. Or int. Same thing as saying int x. Okay. How about this guy? Let's go ahead and we know what it looks like, right? This is the stair step. So greatest integer. What if I input a 0? What do I get back? What's the greatest integer less than or equal to 0? 0. So if I go out to approaching 1, it stays at 0, but when I get to 1, what's it do? Jumps up. Good. And then same thing, it jumps up when I get to 2, right? And then we could do the same thing for negative values, right? Et cetera, et cetera. Okay, there's our function. Well, let's calculate the derivative at 1.5. Okay. So, what is f prime of 1.5? So, we're just going to use, might as well just use, how about, I think it would be no problem to use that one. We can just use our basic one, it should be fine. Either way should be fine. Either that's gonna be a problem. No, it's fine. So, yeah. So what are we gonna get? Should we do this? Yeah, we're just gonna get the limit of f of x plus delta x minus f of x over delta x. Delta x goes to 0, right? Okay, well, what's x in this case? 1.5. Okay. So we're just going to get something like the limit of f of 1.5 plus delta x minus f of 1.5 all over delta x. Delta x goes to 0. Oh, jeez. Hey, Kim, what's up? I think it's 182.5, I think. Yeah. I think that's it. Pretty sure. Yeah. Alrighty. You betcha. Okay, so So then what do we get? What is our function? This is absolute value function, right? So what, I mean, greatest integer. What's the greatest integer function of 1.50000001? 1, right? Okay. So I'm gonna get 1 minus, what's the greatest integer function of f of 1.499999999? 1 over delta x, right, as delta x goes to 0.
Why did you get rid of the delta x at one have the delta?
Well, because, up here you mean? Well, because we can evaluate that, right? It's just 1.5 plus a smidge, to be technical, is just gonna be, actually that's just 1.5, isn't it? Of 1.50001, we're gonna get back the greatest integer function, still just gives us back exactly 1.
So delta x is never gonna be like a whole number. Like
Well, I mean, if it were, it wouldn't be very meaningful, would it? Because then, right, if we're trying to, if this is our point, right here, that we're trying to find the slope at that point, if delta x is macroscopic, then I'm still dealing with a secant line, right? We want to take the limit as delta x gets really, really small, right? Does that make sense? So once again, technical terms, just needs to be just a smidge, right? Okay, so then everybody agrees that's what we get on top? So what's that equal to if I evaluate this?
Absolute value of -1.
Well, 1 minus 1 is
0.
0. Okay, what do we get on the bottom? Delta x approaches 0.
0.0000.
Ah, okay, yeah. We don't
Positive
really
shit.
get 0 on the bottom, do we?
We don't.
See what I'm saying? Because delta x never actually gets to 0, right? You know what I'm saying? Delta x could be, we didn't say what direction we're approaching 0 from. But does it matter? We'll just call it 0 plus or minus. What does that simplify to?
Plus or minus.
No,
Just be 0.
it's 0, isn't it? Because think what I've got here. I've got 0. It actually is 0 divided by some number, albeit small. 0 divided by a number is by definition
0.
exactly 0, right? And so it works, right? As we knew it would. Tells us that the slope of the function here is 0. It's flat, okay? Let's try this at a more interesting point though. Let's try this at something like, how about at x equals 2, okay? So, actually, I don't probably have to go. Oh, maybe I can just do this. Okay, let's do. Okay. I can see, okay, this is, yeah, I can see why maybe this is gonna be a little bit tougher. We can still make it work, but we might wanna use the other form of this. If I put in 2, I'm gonna get 2 plus delta x of 2, right? So if we're assuming delta x is approaching 0 from the right, which we usually do, we'd be putting in a small number that's positive. We're gonna get the same result, aren't we? Isn't the greatest integer function of 2.001 just 2, and of 2 is 2, right? So if we were to push ourselves only to the right, we're gonna get an answer of 2, right? But what if delta x is negative? So if we're approaching 0 plus, from the plus side, this is going to give us back 2 minus 2 over 0 plus, which is 0, right? That's not very interesting, though. Let's look at it from the other side. What if we're approaching, what if we're approaching from the left? What's f of 2 plus a small smidge, negative smidge, 1.999 something, right? Everybody see that? So what is then, this is gonna look like 1.9 repeating-ish, right? So what is f of 1.9 repeating-ish? 1, right? So this is gonna give us back the limit of 1 minus 2 over delta x as delta x approaches 0, call it minus. So yeah, now what do we get? Over
Minus
0 minus. We don't really, it doesn't really matter to us honestly if this is minus or plus, what's the consequence? Undefined, I get infinite, right? And so that's not a number. This is telling us undefined because that tells us if the slope is infinite, that's like a vertical line. We always said, what's the slope of a vertical line? Undefined, right? And so what do we find then? Does the derivative exist there? It doesn't. We can conceptualize that because as an ant approaches 2 from the left, the ant is seeing as he gets closer and closer to that point, his secant line is approaching a value of infinity. As the ant walks backward from the right, he's just seeing his secant line is approaching a tangent line that's horizontal, right? Once again, they don't agree, right? So where's another place where functions are not differentiable? It breaks in the function. Yeah. We get another one for free. What about if we had like a vertical asymptote or something? We couldn't really calculate the derivative of a function if a function doesn't even exist there, right? And so obviously, if a function is discontinuous, we're also not going to be able to take a derivative. There's one other that I'm just going to go through graphically. What's wrong with this picture? What if we took something like cube root of x? It'd be fine every place except there's one place where we'd have a problem. Yeah, we'd have a problem here, wouldn't we? Because what's the tangent line look like?
Confusing. Straight up.
Ah, the tangent line is vertical. And so once again, we have a problem because vertical lines, the slope is undefined, right? It'd be infinite. So we've got really 3 places. Sharp corners, breaks in the function, or vertical tangent lines. But then also, any place where the function is undefined, we'd have an issue, right? Does that make sense? So if I even did something like, like if I had, just say a vertical asymptote, not going to work. Even a hole in the function is not going to work, is it? How could I define a slope and a hole in the function if the function doesn't exist? I was about 2 minutes away from being completely done. We'll wrap it up tomorrow and you guys can work on this stuff. Okay, I got 2 assignments up you can start on for 2.1.